Good afternoon, everyone. Today we'll be presenting our upgrades to the U.S. Air Force VHG Mark II, the mechanical heating claw, and safety shield with optical access to the test chamber. We're Team 5. My name is, we have Kathleen Oyola, Louis Sanchez, and myself, Dennis Leclay. So today we'll be going over an introduction to the project, an overview of our heating system, an overview of the safety shield, a cost analysis, a little bit about our design experience, and a conclusion to our presentation. The VHG Mark I is a testing device used by the U.S. Air Force at Eglin Air Force Base to test fusion components, to shock test fusion components for ordnance and military munitions. The problem that the Air Force is facing right now is that there's no thermal control for the test chamber. And right now they have to put the test fixture in an oven, run across the room, put it on the device, and start the test. And the safety shield doesn't have an optical access, so if they want to use a camera or a laser vibrometer on it, they have to run it with the safety shield open, which presents a health risk to everyone in the lab. So our motivations for this project are to deliver an efficient upgrade to the Air Force, to work with professional engineers such as Aaron and Jason, our contacts at the Air Force Base, and to compete against other universities because we're young, we're competitive, and we want to make FIU look good. The objective of the project is to develop a heating system which will bring the test fixture up to 105 degrees Celsius as quickly as possible, as well as to create a safety shield with a safe optical access to the test chamber. So here you can see the VHG Mark I and the test fixture. The way it works is the test fixture is placed on the carriage yoke, and the chamber is pressurized to 100 psi, and a piston is fired into the bottom of the carriage yoke to produce a shock test. So we split up our roles into major and minor roles, with the entire team heavily involved in designing simulation, the heating system, and testing, and the other roles more unequally distributed. We began the project in September with our team formation and completed our testing and report about a week and a half ago.
So our proposed design for the heating system is a mechanical heating claw made of aluminum. It has adjustable diameter because the testing piece can be 6 inches or lower. So we have adjustable heaters, which are mica stripper heaters. So the main components of the heating claw are 2 rotational pieces with the holding panels that are moving, holding the heaters. So you can move the panels. And then we have a mounting claw connected to the mechanical stand, which has an arm and a pole, so you can move the claw in every direction. Also a moving base beside the heating system.
For our mica strip heaters, we ended up deciding to go in for Temco mica strip heaters because they provide great emissivity and conductivity. These mica heaters, they can go up to 650 Celsius. Also, they are custom manufactured to our design specifications with a cross-sectional area of 6 inches. Reason why, because the U.S. Air Force Laboratory, the biggest piece that they have is a 6 inches diameter, outside diameter. So we wanted the heating pass to have full contact with the testing piece. Also, each of our mica heaters have a 250 watts, making the whole system total for 1,000 watts, and we calculated our watts with this formula, as you can see. Our simulation. For our thermal simulations, we did simulations in a 6 inch diameter testing piece and a 4 inch diameter testing piece. We also did static studies on our mechanical stand and under 7 different scenarios. As you can see here, we have our thermal study for our 6 inches. Our heat power was 250 watts per heater. Our initial value of no insulation and initial temperature of 23 Celsius. As you can see here, we did in 4 different steps, 200 seconds each. At 200 seconds, we were at the testing piece was able to reach 71 to 84 Celsius. By the time it hit 600 seconds, our testing piece already passed the goal of 105 Celsius. So around 420 seconds, we'd reach 105. As you can see here, our mica strip heaters are in 194 Celsius, while the average of our whole entire testing piece was an average of 136 Celsius at 600 seconds. In this one, for our 4 inches, it's a little bit different because now the mica strip heaters and are only working as conductivity. They're working 70% as conduction and 30% as radiation. So we also did in 4 different steps. As you can see, at 200 seconds, our testing piece reached the 50 Celsius, and at 600 seconds, we were able to reach our goal of 105 Celsius. And here you'll be able to see the difference between the 2 testing pieces at the time it took to heat up. As you can see here in the red one is the 6 inches and the green one is the 4 inches. In the 6 inches, it was faster the heating time because the mica heaters were fully in contact with the testing piece. So it was working in conduction. But both pieces were able to heat up in less than 10 minutes.
We also conducted static studies on the mechanical stand. We did it in 2 positions, the standard operating position and the completely unrealistic, fully extended position with the arm completely extended and at the max height. We also did it with various loads horizontally on the post clamp and vertically at the tip of the claw. So from our results, we found a wide range of stresses, all beneath the yield strength of steel. And we found a max deflection of the tip of the claw under standard conditions of about 9 millimeters, which we found was in our expectations, with a factor of safety of about 3.48. One note about our simulations is that the base was fixed, when in actuality the base can roll. So horizontal force will push the stand across the room instead of just bending the pole. After doing our simulations, we focused most of our testing on the heating system because that was the main component of it. And we found with a 6-inch diameter pipe, we reached the desired temperature in about 180 seconds. You can see the first trial is a little off because we just set the heaters to the max temperature, and after a few tests we found that was a lot less efficient than slowly increasing the temperature of the heaters. So for the production of the prototype, it was a combined effort between the team. We also had Professor Zigarelli help us, and we contracted out a few of the parts to some local companies to create components which we couldn't do by ourselves.
So our proposed design for the safety shield is a little bit different than the safety shield from the Mark 1. This is rectangular. The Mark 1 is cylindrical. Also, the thickness of the Mark 1 is 0.25 inches, while this one is 0.1875 inches. That's because there are not going to be more explosion testing. So it's going to be made out of aluminum. And also we have an optical window, 1/8 of an inch thick, which is virtually unbreakable. So the simulations, we did 2 simulations, static studies and drop test studies. Static studies reveal long-term damage after thousands of impacts in the same position. So drop test study reveals more realistic values after the chip impacts. We studied 3 different pieces, which is the safety shield body, the window, and the top that is removable. But only the window and the top are the most important, as requested by the Air Force, based on chip impacts. So for the drop study for the optical window, the simulation, we use a momentum formula. The mass of the impacting chip times the velocity at the impact is equal to the mass of the object times the velocity that it should have on the drop test to create the same momentum. We have different cases. Those are unrealistic cases pushing the limits of the window for this scenario. However, there is barely deformation, 0.04 millimeters in the worst case scenario for the window. For the top is thicker, 0.25 inches as requested by the Air Force because it's the piece with the most probable full chip impact. And however, we have again different scenarios where the worst case scenario is 0.008 millimeters deformation. So it never breaks through as the Air Force wanted. They don't want it to break through. It never breaks through in any possible chip impact. So we did an experimental testing. We did a drop test study. We went 5 meters high and we dropped different pieces of different masses higher than the chips to create the same or similar momentums. And it never broke anything, no scratches, no fissures, not even with a piece of 50 grams, which is that one, which creates a momentum 4 to 2 times higher than the worst case unrealistic scenario for the simulations. So we are pushing the limits of the window and it never breaks. So the prototype is made out of wood due to funding. It's thicker than the real one. We have different brackets, hinges, removable top. So simulating the real safety shield.
For our cost analysis for the mechanical clock, our total came out to an approximation of $2,000. Our most expensive pieces were the mica strip heaters. Reason why, because they were custom manufactured to our specifications and design, as explained before, with the 6 diameter cross-sectional area. And here you have the total for the safety shield. As my teammate was explaining, we were not, because of budget at the time, we were not able to finish the product. But the Lexan window will be the one that is going to be implemented in the product. For social environmental impact, the normal use, the system does not release any harmful gases or chemicals, and all system components can be recycled and repurposed, just like the aluminum, the steel, and same as the window. And our social impact is to improve the testing time and to the airline music technology. For standard, we use the ACM standard, which were used in the production of the aluminum and stainless steel. Then we have the NRM EN 356, which is the European testing standard for glasses, which was for the Lexan window, which is made of polycarbonate, and it actually came out with the higher standards under that category. Also the RIHS for restriction of hazardous substances, and the whole system comply with OSHA safety requirements. For our health and safety, our mechanical cloth design does not represent any harmful, significant health risk, but consideration should be taken while handling the system because of the size and the weight. Testers should be careful while handling. Also, our Lexan window, the Lexan optical window, when exposed to higher temperatures, higher than 100 Celsius, it can create gases that can cause irritants. Can be irritating for a respiratory system, but our window will not be exposed to higher temperature. It will always be at ambient temperature. As well, after testing, the heating cloth will be hot. That's why we implemented the 2 handles right on the side, so you can see. This one will not be heating at the same rate as the rest of the system, so they're safe to be handled from there.
So for our global learning, we have different aspects. As a global perspective, this aims to improve and reduce the risk of undetonated components, which in many countries some undetonated components have gone unnoticed and after many years have detonated, representing a risk for the society. We also have global awareness, in which we include SIE and English units in the report, as well as a multilingual user manual in 4 different languages: English, Spanish, French, and German. Also, we have a global engagement because we are 2 different teams working on the same project to find a solution for problems faced by the Eglin Air Force Base Research Laboratories. For our lifelong learning experience, we have obtained a wonderful, good experience that is going to be very useful for our future mechanical engineering careers. By working in engineering teams in a small and large scale, basing our designs in commercial and manufacturing ability, as well as working with professional engineers, contractors, external companies that have helped a lot in this process to accomplish the task. So our future work, we would like to manufacture the safety shield out of aluminum and test it, as well as do an automation system for the mechanical claw, which includes a software program to make the work easier for the testers. As well as my teammate said, these heaters are interchangeable, so we can purchase and design different heaters for the specified testing piece, all the testing piece, so we improve the efficiency on the testing time. So we would like to thank you to Professor Richard Ciccarelli, which has been a big help in the manufacturing process and guide us in every step. Dr. Tosunoglu and Dr. Tansel, which have been our advisors during this whole project, as well as Jason Foley, Erin Silva, and the United States Air Force Base for their support since the beginning of the project.
So that's our presentation. If you have any questions, we'd be happy to take them.
If I may start off, several of those components will be subjected to dynamic load, correct? Yes or no? Okay, so to what extent have you assessed the the endurance of those components to cyclical load as it relates to potential fatigue failure within a certain period of time?
Well, we didn't really focus on that because most of the time the claw will be stationary. The only times it will be under dynamic loads is for the small movement to the device and away from it, but
But what about the impacts?
oh no, the impacts are not on
This
the
piece
claw.
doesn't experience any type of impact. However, the safety shield, the window, there were two parameters. One, it was try to hold any impact, it never breaks through. But however, if in the long term it has scratches or some fissure on the surface, this window is commercially available. You can order in 1 day and have it in 2 days as requested by the Air Force Base. And as well as the top is thicker as they requested. The only thing they want is never break through in one impact. If it breaks any scratch, any fissure, it can be replaced. The thing that they want is in one impact, it doesn't go through any chip away from the laboratory. And all our study and experimental testing revealed that it's not going to break in any impact. And in the long term, it can be replaced if anything happens. However, our simulations reveal that it should work perfectly for at least a very long period of time.
My question is, I'm trying to get a handle on this. So that heats through the center of the pipe there?
Yeah. This
Through
one,
through the lower diameter pipe,
yes,
right?
correct. This one will be surrounded this way.
And then
this
you
one
heat
will
it
hold-
before you put it in there? Or
No.
you heat it while
While
it's
it's
in there?
in there.
While
This
it's in
testing piece, I'll show you. This testing piece, it will be right here, folded.
And
this
closed
one-
in that and with that in there as well. Now, why do you think the heating was better when you went slowly as opposed to fast?
Okay, the heaters, the way that it work, they work depending on the thermocouple temperature that it says. If the thermocouple says 25 and you want to go to 105, the heaters, they work really fast. They start throwing a little bit of smoke. They work, but you reduce the work life of the heaters. However, so
You said more efficient, not more life, but, so you're saying you got a better temperature when you went slowly than you should put it full
exactly,
blast?
if it goes slowly,
I mean, so why do you think that happened?
I don't know, I would say like overworking, because when you overwork this heater, they start throwing smoke and
I mean, what about the contact point where it might have to do with a contact point within the metal and the other metal, or there might be a gap there, I'm not sure.
Well, is that thermocouple a feedback to it? Is that what it is? It's feedback control?
yeah.
Is that what it is?
So what it probably is, it's probably detecting a high ambient temperature and actually turning them.
Oh, okay, so it's actually
Self-regulated.
self-adjusted. A while back on my research, what I did was, I don't know how the resistance is on that, but I actually had an arc welder, and I was running the current through the actual thing to increase the temperature on that, but I don't know if it'll work. But that's just for the heating, right? The cooling was the other guys.
cooling work.
The cooling is a different system.
Now, you said something about detonation of ordnance and stuff. What does that have to do with this?
Oh, well, like the other team said, the shock tests are on the fusing systems for the explosives. So if the fusing systems don't work.
Oh,
the
I see what you're saying.
explosives-
So it's gonna be more efficient, it's gonna go off as opposed to not going off, okay?
Yeah, so it'll go off when it should go off.
I thought you were talking about the stuff that's there now that's didn't explode. Okay.
Can you talk about your impact simulations again, or I guess you did analytical studies? So you used law of conservation of momentum to do that impact?
Yeah, and that was after some research and some talks with, for example, Professor Tansel. He recommended to you to the way of testing this window. It was by a drop test study using a momentum formula. Because in the installations here in FIU, we don't have anything to shoot at this window at 50 meters per second. So that was the more realistic way.
So just really quickly, you drop,
Different
can you go back to that slide if you don't mind? Just go back quickly. So, the next one actually is.
No.
No.
The other, forward, there, nope. Yeah, all right, perfect, there we go. So in this case, you're not dealing at all with penetration of any of the chips. The chips are really small, right?
The chips, the real chips in the experiment is going to be
Very-
0.0001 gram, like
Right.
it's really small. So we wanted to push the limits by using chips of 1 gram, 2 grams, half gram, going at the maximum velocity, which in reality is never going to impact at that velocity. We wanted to push the limits to see if it breaks.
Look, I understand that, but I don't know necessarily that this data gives you that, right? I mean, law of conservation of momentum is for things like impacts in space, where you have one rock hitting another rock, right? Or whatever. This is a penetration problem more than anything, right?
Well, I mean, for that we designed different logs, which has like a stopping distance. So
No. Again, so you have a small thing hitting a table, right?
Yes.
The table is not going to move away at any noticeable velocity because the two masses are so much different, right? But a small thing can still penetrate through the table, correct?
I mean,
I'm not talking about your system. I'm talking about in general, right? Two things can happen. One, the entire thing can move, or the small thing can go through the big thing, right?
Mhm.
Did you look at all at the small thing going through the big thing? Because that's the more dangerous situation in this case, right?
Yeah. No, I mean, after some talks, they said this type of thickness for the aluminum. The research on all the window, it never suggested chips of that size and that velocity will gonna go through these pieces on the experiment.
Okay.
Greg, did you have a comment?
No.
No? Aaron? Ian?
Just very quick question. Just very quick question. In your global discussion, you talk about using English, Spanish, French, German. Why those languages and why not some other languages?
Well.